Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome back. Okay, now let us solve a one practical problem which is the short shock tube. Okay. So, this we have already discussed earlier in the context of finite difference simulation. So, on the left you have the high pressure and right you have low pressure, okay, and we will be using the short shock tube. So, basically your PL and PR. So, the ratio is basically 10, okay, and rho L and rho R is basically ratio of 8, okay, and U L equal to U R equal to 0. Okay. So, this is the problem that you are working on, and at t equal to 0 the diaphragm breaks, and what will happen that your shock will travel on the right side and expansion will travel on the left side. Okay. So, this is the typical problem, and we know that for the Euler's case, okay, that is the inviscid case, we know the exact solution. Okay. So, we choose this problem always because we know the exact solution and we can compare our solution with the exact solution. Okay, these are the definitions. So, I have taken 1 and 0.125. Okay, you can, if you solve in dimensional form, you will can take appropriately. Rho L you can take maybe 1.25, P equal to take 1 atmosphere, and still you can solve it. Okay. So, here I am taking non-dimensional form. So, rho L is 1, P L is 1, U equal to 0. Okay. Convert from the primitive to conserved, conserved to primitive, and so on and so forth. And finally, we also saw how to calculate fluxes, right. So, if you have all this value, you can calculate fluxes easily. Okay. So, how we are going to solve it? We are going to make a grid like we always have been doing. Okay. So, we will consider a domain of 0 to 1. Okay. We will at 0.5. Okay. On the right hand side we will put the condition for the right, the left hand side we will put the condition for the left. We will be using the cell centered finite volume. Okay. So, not the vertex centered. So, let me make this is my boundary and this is my boundary. Okay. So, I will basically divide into many different parts. So, these are my cells, and on these cells we have basically the cell centers. I will show you the code very shortly. Okay, these are the cell centers. Okay. Now, these are we have to apply the boundary conditions here, right. Here, so we have to apply the boundary conditions here. So, what I will be doing, as we discussed last time, will be making a ghost cell. Right, these are my ghost cells. Okay. So, let us say if you have using cells. So, first let us say faces, right. So, the is like the finite difference formulation. So, like divided into 101 parts. Let us say you have divided into 101 parts, you have 101 faces. So, cells will be actual cells will be 101 minus 1 will be 100, right. You can count it here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, right. And if you count the faces 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, right. So, the one extra face, okay, is only in valid in 1D. Okay. In 2D or 3D depending on what kind of elements you have, you can have mixed elements also. This is another thing that you should know, that it is not necessary that you only use the triangular or the quadrilateral or maybe the tetrahedral or hexahedral, you can mix it. Okay. You can have different kind of elements, and typically in finite volume you have mixed elements. Okay. So, and also like let us say if you are doing let us say flow over an aerofoil. Okay. So, what you can do, you can have very nice prism elements or element which are basically close to the body respecting the boundary layer like this. Okay. And then if you go away, okay, so let us say this is your domain like this. Okay. So, you can have the very nice grid near the body, okay. And of course, when you go away you have to match to the boundary that you have. Okay. So, what you can do, you can put some very nice pointillier grid here. Okay. So, in 2D it is a very nice quadrilaterals. Okay. But you have to match to the outer boundary. So, what you can do, you can have like grid which is just basically growing, matching the boundary, any kind of grid. Okay. So, you can have unstructured grid completely outside. Okay. The only thing that you need to take care that you cannot have the overlapping elements. Okay. Similarly, here you can do whatever you want and basically go to your boundary, right, and you can fill this in the entire domain, right. So, here you have very nice quad elements, here you can have triangular elements, you can have pentagons. Okay. So, the number of faces on each cell will be different. Okay. So, you have to basically take care of your number of faces, okay, number of cells when you are making grid, and number of nodes or the vertices. This is important particularly in viscous calculation, okay, because you need to get the gradients also on the faces. Okay. So, in 1D your number of cells is just 101 minus 1, number of faces minus 1, which is basically 100, and then if you include the ghost cells. Okay. So, total cells is equal to cells which is internal cells plus ghost cells. Okay. So, I am taking only 2 ghost cell. Okay. This is let us call it ghost cell 1 and this is ghost cell n plus, this will become. So, this is 1, then this will go to 2 to n, okay, and this will be n plus 1. Okay. So, cell plus ghost cell will be 100 plus 2, this become 102. Okay. After we created our data structure and we have basically now what we will assign that my rho L for like x less than 0.5 is 1 and rho R which is basically x greater than 0.5 is 0.125, and similarly you can do for pressure also and velocity also. Okay. So, we have assigned the values. Now, comes the first thing is reconstruction, right. So, for all of these we have to basically do the reconstruction. Okay, from the left cell and from the right cell you have to get the value to the cell face here. Okay, this is my cell face, and then we will use a scheme in this particular scheme is a Lax-Frederick scheme, okay, which I have discussed many times. Okay, but you can use row scheme, you can use HLLC scheme, any scheme that you want. So, you have basically the condition which is UL and UR. Okay, let us use small l and small r. Okay, so, this is coming from the left and this is coming from the right. Okay, this is my UL and this is my UR, right. So, once you have the UL and UR, you can use your favorite scheme and get the residue. Okay. So, up till now this is fine. Now, one issue that quite often happens is the like once you are trying to reconstruct. So, depending on how you calculate the slope. Okay, so, what may so happen, let us say this is our function, okay, and we are calculating the value, this is my face, this is my face, okay, and if you start calculating the gradient, okay, basically del u by del x. So, let us say this is my cell and you will calculate the gradient, you will get the gradient which is going like this. Okay. So, this is basically my du by dx which is going positively. Okay. So, if you reconstruct if you reconstruct and go to the face, your new value that is coming is this much, okay, u plus del u by del x, but actually your value is quite low, right. So, in these particular cases these kind of cases which is very common in finite volume, what will happen is that you will start getting oscillations because you have actually jumped over the local maximum. This is my let us say local maxima. So, your reconstructed value is actually above the local maxima, right. Similarly, what may so happen that you are going basically undershooting the local minima or you are overshooting local maxima. So, if you have anything like this, then what will happen is that your solution will not converge, or it will blow up also, okay, and or it will give a lot of oscillations. Okay. So, we need to use some kind of limiters. Okay. So, that is where the concept of limiters come in. Okay. So, that we need to ensure that we are not basically overshooting the local maxima, or basically undershooting the local minima, going below the local minima. So, the job of the limiter, there are many kind of limiters in the literature. There is mean mode literature, okay, mean mode limiter, then you have Venkat Krishna limiter, okay, VK limiter, okay, Van Alberta limiter, VL limiter. Okay, so there are different kind of limiters. So, their job is to basically ensure that the gradient that you are getting is basically not overshooting the local maxima minima, and by doing this, what they ensure is something called these schemes become total variation diminishing. Okay, or it is called TVD, an essential property for a solution, or for a simulation to converge. Okay, and we have TVD temporal schemes also, so that you do not overshoot in time also. So, that you have TVD in time also, this is in space. Okay. The other extreme case which may happen is that, let us say you have some values like this, okay, your one cell here value here, one cell value here, okay, and you calculated a gradient which came like this. Okay. So, this is your cell center. Okay. Now, the next value is below 1, okay, much below your left cell value, but we are getting the gradient which is positive, and that is why your reconstruct will be somewhere here, right. So, these kind of cases are not acceptable, because you are going above the global minima. Similarly, if you look at the gradient here also, okay, and let us say you want to use the value, this is my right cell, this is my left cell, and this is let us say my phase f. You want to calculate the value from here to the gradient here. So, this will go in this direction, and here it is going on the right hand direction. It is actually overshooting the, this is an overshoot and this is an undershoot. Okay. So, in these kind of cases, what you do, if you are getting a positive gradient and your right hand side has got much lower value. So, what you do, you just make the gradient to 0. So, basically your del u by del x becomes 0, you force it to become 0. Similarly, in this case also you will force it to 0, because it is undershooting. Okay, this is not I mean I am considering this particular cell, okay, I mean this particular phase f. For f, let us say f plus 1 here, you may have a different case, let us say your f plus 1 value is like this. In that particular case, this gradient is acceptable. Okay. So, we have to ensure that our scheme is total variation diminishing. I will show an example that if you do not use a limiter, okay, then what happens. Okay. So, let us start looking at the code. Okay. So, the code is very similar to what we had in finite difference. Okay. So, this actually I picked up, it is a group in Singapore which I developed this code, okay, a person in Singapore, but it is very easy to write this code. Okay. So, let me stop here. Okay. So, you can see that I let me just make a little big. Okay, so, my length is 1, Lx equal to 1, and the discretization I have is from dx by 2, right. So, I am starting point is not 0, it is actually from dx by 2. So, it is the cell centered schemes, okay, and these are my initial conditions, okay, and I initialize the arrays, okay, rho 0, u 0, p 0, and if it is left, then you put the conditions on the left. Okay, if it is right, then you put the conditions on the right. Okay, you do it for rho, you do it for u, and you do it for p also. Okay, you can calculate the energy and the speed of sound using the formula that we have. Okay, and this is the exact solution which I have already seen earlier also. Okay, now basically what we need to do, we need to put the ghost cells here. Okay. So, when you are putting ghost cells, we are putting a ghost cell on left and right both. Okay. So, this is nx equal to nx plus 2, right. So, we have increased the array size by 2. Okay. We will reduce it again while plotting, and then we have this array of the conserved variables, okay, rho, rho u, rho e, okay, and then we have to basically pad the left cell and the right cell with the ghost cell. Okay. So, this is my q 0 and I padded 0 0 0 value just to give the boundary conditions in the ghost cell. Okay. Now, you give the boundary condition in the ghost cell. Okay. So, it is in this case it is actually trivial. So, we are just using the Neumann condition. So, basically the gradient goes to 0, okay, and 1 on nx both. Okay. These are conditions. Now, we can basically use the variable time stepping. So, calculate the lambda, which is the total velocity, which is u plus a, here absolute u 0 plus a 0. Okay. Based on that, you can choose a CFL number. I think I have chosen around 0.45 or so. Let me just see. Yeah, I have taken 0.5. Okay. So, you can take the value of 0.5 here, okay, and calculate your delta t based on the CFL condition. So, C delta t by del x equal to 0.5. So, you can calculate the delta t. Okay, this is the initial, and as your value will change basically u and a, you can calculate the update the value of dt. Okay, initial conditions we have taken. Now, go to the solver loop. So, now this is where we calculate the residue. This is Lex Frederick residue. Let us look at that code. Okay. So, what we are doing? We are using the Euler forward. Okay. Basically q minus q naught by delta t is equal to the residue. So, calculate the residue and just multiply by delta t and subtract from the older value, right. Now, the main trick is to look at the residue. Okay. So, first look at the residue function. So, this is the Lex Frederick flux. Okay. So, you know the conditions at left and right. Okay. I will go that how do you get, these are the reconstructed solutions at the face. Okay. This is QL and so on and so forth, and these are the right state, and from that you calculate the fluxes, and finally, this is basically your C delta t by del x, okay, delta t by del x, okay, and multiply by QL minus QR, right. This is the typical Lex Frederick scheme that we have been using. Okay, there we were using I plus 1, I minus 1, here we are using left and right condition, update condition, and we will be calculating the fluxes. Okay. So, once you calculate the fluxes, you have to calculate the residue. Okay. So, before that, how do you get the value at the faces constructed from the left and from right? Okay. So, you can use this forward difference. So, you have j plus 1 minus j, so forward difference. You can calculate from the left, which is the backward difference, and this limiter is called the mean mode limiter. So, what it will do that it will consider both the gradients from both the sides and give you a unique gradient here, okay, from the mean mode limiter. I will show that what happens if you just say take either the forward difference or the backward difference without considering the limiter. Okay. So, right now I am using a limiter, which is what it is doing. We have constructed a value from the left, we have constructed a value from the right, and we got one unique value. Okay. So, we got the gradient here. So, you basically add it on the left and subtract it from the right, okay, and you get this QL and QR value. Okay. Take the j plus 1 value and subtract the gradient from there, take the j value and add the gradient from there, right, and you get the flux. Okay. Now, we are using loop over faces. So, this is my left face, we will add the flux on the left face to calculate the residue, to get the residue, and we will subtract from the right cell to get the residue. So, if you do it over all the faces, so we are ensuring that each cell is the values in each cell is locally conserved. Okay. And then these are just the boundary conditions thing that because on the leftmost face when you are calculating the gradient, you have to be little bit careful because this is only delta x by 2. So, that is what I am doing here, and calculating the flux on the left hand side. Similarly, you can calculate the right hand side flux also. Okay. And this is the mean mode limiter, which is basically saying that if it is exceeding, then put the gradient to 0, otherwise you take with the appropriate sign. Okay. So, S is basically is the sign and take the minimum of those two gradients and use the appropriate sign. So, this is the mean mode limiter. Okay, now let us run this code. Okay. Okay. Let me run this code. Okay, you can see probably the screen here. So, it is getting so this is the convert solution that you got. Okay, at a given time, I think I have taken the time as 0.15 second. You can take 0.1, 0.2. The only thing that you need to make sure is basically it is not going outside the boundary. Otherwise, you have to take care of your boundary conditions more carefully. Okay, so you can see that this is how it comes. So, I have plotted so the density is there, velocity is there, pressure is there, and I think this is internal energy. So, all four things you can see here, and finally, this is the, let me just see if you can. Okay, I think it's too big here, but you can see that it's following the solution quite accurately, right. So, density, velocity, pressure, and energy, it's internal energy, all everything is captured properly. Now, let me just do one thing. Okay. So, what I will do, I instead of using the mean mode limiter, I will just use the, let me just use the forward. Okay. So, what I am saying that my dq ij is just the q ij plus 1 minus q ij. Okay. I am not using limiter, I am just reconstructing from the right side ij plus 1 minus ij. Okay. So, if you just, you can take an average of the two also. Okay. Just let me run. You can see that now it has blown up. Actually, you start seeing this imaginary parts and solution is all messed up. Okay. Let me stop it. Let me see if I can show you the solution. Yeah. So, this is, you can see that it has got completely messed up. Let me decrease the CFL number and let us see if we can do anything better. Okay. So, this is your final solution. Okay. You can see lot of oscillations here, and I mean near this shock part, I think the solution is very bad here, right, because right now we are considering the gradient only from the right hand side. Okay. So, you can see that how the limiter plays a very important role when trying to reconstruct the solution. You can try with let us say only using the left one, I think that will also blow up quite fast. In fact, it may not run also. Let me just see. Okay. So, what I am doing, I am just doing the calculating gradient from the left. Okay. It may quickly blow up. Yeah, you see imaginary parts of the complex. So, it actually becomes a complex number. Okay, so this is the issue we have. So, that is why the limiter is very important in finite volume coding. Okay, although it is a very small part, but you have to make sure that you are not overshooting or undershooting the maximum, the maxima, local maxima and local minima, right. So, you can basically extend this problem to 2D and 3D, and you can try coding for a very simple problem like the short shock tube problem. Okay, only thing that will happen is that now you will have x and y both, right. Right now we have just x, it will be I and j both, and it should not be very difficult. So, I will suggest that you go back and code the 2D problem at least and see how it works. Also, you can try different schemes. So, I am showing for Lex Frederick, but you can try many different schemes that you want. Okay, if you can read literature, you can try basically the row scheme and so on and so forth. Okay, so, with that we will stop the finite volume discussion here, and we will start a new topic from the next class, and I hope I gave you a flavor of what happens in a finite volume. Once again, most of the commercial codes use finite volume. Okay, the finite volumes are of two kinds, two ways you can use the finite volume. One is cell centered, other is vertex centered. Most of the codes use cell centered approach, but some codes, for example, is CFX uses the vertex centered formulation. Okay, there are certain advantage and disadvantage of both. So, vertex centered actually uses the Dirichlet condition more forcefully, because you have vertices at the boundary. So, you can ensure or enforce your Dirichlet condition. In the finite volume, it is enforced weakly, and you can use the ghost shell approach. And in all of these, we use integral formulation, which ensures that you have the local conservation as well as the global conservation. Okay, you can use different kind of elements. You can use edge based looping, or you can use the cell based looping. It's all up to you. The finite volume is suitable for any kind of geometry. Okay, any kind of bonding condition, any kind of geometry, you can use the finite volume approach. The only issue it has compared to finite difference is that it may not get, I mean, you may not get very high accuracy, because unlike finite difference, where you can basically extend your nodes on the left side and the right hand side, basically stencil can be big. In finite difference, in finite volume, it is very difficult to do that. Okay, what people do is they actually use the neighbors of neighbors to get a higher order reconstruction. There is another approach like spectral volume, where you basically try to have the higher order elements within each cell. Okay. So, all these things are possible, and then you have something called if you go to finite element, then accuracy like P and H, right. So, you increase the polynomial size. So, each cell is defined as a polynomial, okay, and H is basically the size of the grid. So, you can, if you are decreasing H, basically what you are doing is you are making a more refined grid, okay, or if you are increasing P, that means you are increasing the polynomial of a given cell. Okay, so these are some concepts which you would need when you start doing coding. For finite difference, finite volume, I think the edge refinement is what we see, is that we keep on refining the grid, and we see that whether we are getting grid convergence or not. Okay, the P refinement is generally not applicable in finite difference and finite volume. Okay, so let us stop here, and we will start a new topic from the next class. Thank you very much.